SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the NPTEL course on groundwater hydrology and management. This is week 1, lecture 5. With today's lecture, we would be completing the first week, wherein we looked at the introduction of groundwater hydrology, some concepts of groundwater and why this course is important, how the course is structured, and what you need to take away from this learning. Let's continue from where we discussed in the last lecture. We stopped at the system's representation of groundwater hydrology as a flow chart. So we said precipitation can come in after leaving some losses for interception and interception storage. Part of the precipitation goes through fall and hits the land surface. Once it hits the land surface, the water is available for infiltration. Infiltration is also driven by the gravity because gravity wants to pull things down. Same from the atmosphere, rainfall comes down because of gravity, and then it hits the land, pulls more gravity to further move the water down. So infiltration happens. Part of the water goes as overland flow, which means the water goes on the surface and goes into the oceans, rivers, whatever is nearby. And then the infiltrated water goes into the soil, converts the soil from unsaturated to saturated. What is unsaturated? The soil and rock media has porous space in it. And when water moves down, water will push the air and fill it with water. Not all air can be driven out, but it can be pushed and then water takes up the space. Soil also attracts water so that plants can take up the water for evapotranspiration, and trees also and other living organisms like worms under the ground. So once this soil profile converts from unsaturated to saturated, you slowly hit the groundwater table and the groundwater recharge. So below the groundwater table, all the porous space is full of water. So groundwater recharge further into this aquifer or the groundwater table will raise the groundwater table. So now you see a raise in groundwater table. So this precipitation has converted through the infiltration into the unsaturated soil and then into the aquifer, groundwater storage. What happens to the water? Because of water wants to be in the most stable potential, it will try to see if it is in a high potential, it will go to a low potential until it is balanced. The oceans, lakes, etc. are sometimes at a very low potential, especially the sea is at a zero potential. So water would start to move, and that contributes to base flow. Some soil moisture would contribute to interflow, and then you have your overland flow, all combined together in the channel storage like rivers, streams, and goes out as runoff. You have some of the water taken up by plants, which go as evapotranspiration. Let's look at the base flow concept. This is what I wanted to continue from last lecture. So your water table, which is your height of your groundwater level, has porous media. You see it in dots, and it is not a river. So a river is like this where there's no dots. A stream is like this, and there's no dots. So this is surface water, this is groundwater. In groundwater, you still have the solid phase, the solid particles. Water flows through it. It can only flow when the water table is achieved. So you could see the water table is achieved and water moves. Where does it move? It moves to the stream. The arrow marks show it because your stream is at a low potential compared to the high potential in the water table. So water flows from high to low potential. Same here. But in this case, let's finish this case. You have trees and agricultural area. So you have better infiltration and plants taking up the water. but more important, because you have infiltration high in an agricultural area or a forested area, water can recharge fast. When you come to a desert system, you still have a stream. Your stream is there, but your recharge is less, maybe because of high temperature, low rainfall, and or the infiltration is not happening as good as in your forested area, because you can see cactus. Cactus is seen in deserts. So that is an indication of low rainfall. So what is happening is already the water table is much, much lower than the stream level. So now the stream water potential is high and groundwater is low. So the opposite happens, which means from the stream, the water comes down. So when base flow occurs, it is only from groundwater into the stream. But that doesn't happen always. The stream can also contribute water down, which is called recharge. We'll just look at base flow for now. So understand the concept of base flow, wherein we have water table and the water table is at a higher potential, so it has to give in to the stream. Moving on, we also would discuss in the lecture series a base flow separation to understand the component of base flow in hydrograph. Okay, so what we do actually is we look at a time series of discharge in the stream. Discharge is the water flow coming in the stream. You would have a peak happening when the rainfall is done and the peak rainfall is done. So you have a low discharge, then a climbing limb wherein the discharge climbs, and at a peak it stops and then comes down. Okay, so this is the peak discharge, the flood top level in your stream. Then it slowly comes down. It doesn't come down fast as your peak is reached, because rainfall is occurring at a high pace. So it comes once after rainfall slows down, the process is slow. So once you come down, what you notice is that your base flow component is already inside your discharge. Let's look at how it looks. So when there is no rainfall, your stream is still flowing. How can a stream flow or a river flow when there is no input to the system? Because your groundwater is giving water, right? So in the previous diagram also, you didn't see rainfall on the top. Groundwater is flowing because it is at a high potential and low potential. It has nothing to do with your rainfall. So that is what is happening. So this line is your base flow. When there's no rainfall, you still have discharge. But as soon as rainfall picks up, the base flow component goes down. Why would that be? It is because when you raise your level in your stream because of rainfall. So when rainfall comes, the river level goes up. This level would go up. So once it goes up, it is at a higher potential compared to the groundwater. So initially it was like this. The groundwater is giving water into the stream, but now your stream level is high. It gives to the water. So, or pushes, it gives water to the base flow component, or it prevents base flow from giving water to the river. So your amount of base flow comes down because your peak is happening. But after your peak is coming down, slowly your stream level is coming down and your groundwater is coming up. And your groundwater, because groundwater is also recharging because of your rainfall. The same way your stream gets rainfall, your groundwater also gets rainfall in a delayed days, number of days. You can see. So rainfall stopped here, but the peak happened 2-3 days later. And after 3-4 days, your base flow kicks in. So now your stream is at a higher, it was preventing the base flow from coming in. And then slowly your base flow comes down. So now your groundwater comes in. So this can be explained by this diagram. When the peak happens in your stream, your base flow is at the lowest. The base flow contribution into the stream is low. Then after, when the recession limb comes, when your groundwater is being picked up by base flow, but most importantly, after your peak, your stream discharge hits the recession, which means it's climbing down. While it climbs down, your base flow increases and then comes back to the same line. So if you imagine drawing a straight line, it will be the base flow component. But inside, it has come down and gone up. And then again, your base flow kicks in. when there's no rainfall. Okay, so this is called the hydrograph separation method. There are equations for it. What we need to drive out here is all streams, perennial streams, not seasonal, all perennial streams would have a base flow component because not everyday rainfall occurs. So rainfall doesn't directly flow into your stream, but it flows through the groundwater and comes out as base flow. Now the tricky question, how does this look? How does this discharge look in a situation where you do not have a perennial stream? So more or less, it is a seasonal stream. So for a seasonal stream, let me draw it. Your discharge will not start at non-zero, it will be zero. So when the rainfall occurs or before the rainfall, it is zero, and then it will peak and then go down to zero. Okay. So there is no base flow component before. However, there could be some base flow here coming from the groundwater component. And when the peak is attained, it falls into the recession, but again, it goes back to zero. It slowly goes back to zero with your base flow component, but both the discharge and the base flow is zero. That is why you do not see a flow when there is no flow in the river. So the base flow is zero. That is why you don't see a flow in the river. Okay. So moving on, let me put back my spotlight. So moving on, you have the groundwater relocation. Okay. So what is the groundwater relocation? You have seen the base flow component. Now you could also see that groundwater doesn't always have one aquifer or one water table. You can imagine to have another saturated zone below the aquifer. Okay. So I will not get into the detail because this would be a very focused discussion. But what I wanted to get is groundwater is being relocated throughout its journey. So from the precipitation, water is called precipitation when it comes from the atmosphere into the top surface. Once it hits the top surface, it becomes infiltrated water. Then it takes the name as soil moisture, as you can see here. After soil moisture, it gets into percolation and goes into the groundwater. This one and this one. Within the groundwater, it doesn't stay there because of the potential difference. It starts to move. And that movement gives way to groundwater flow, groundwater hydrology. And at the end, it can go to base flow and into oceans or rivers or lakes, depending on where it's situated. And within the groundwater, different layers can be created depending on the layering of the rocks. So suppose you have a layer of rock which is impervious, which means it doesn't allow water to flow. So all the infiltration cannot pass on this layer, so it has to go this way. Same way your groundwater is coming, it cannot go up because this layer is preventing. Same, this layer, aquilute, impervious layer is preventing it from going down, so it moves laterally. So you have two lateral flows because of the presence of an impervious layer. So groundwater relocates. It relocates to the place where it has less resistance and where it can flow. So with this, I would like to recap the week one. Okay, so you've seen the introduction to the course as why we need to study groundwater as a resource, why we need to study groundwater hydrology. Okay, let's do a short recap. We did the course introduction on why it is necessary, and especially for India. We did some examples of a case for in India, why and how much we extract. We looked at a particular state to look at how much water is available, how much water is the demand, and what is the stage of development. We also looked at course breakups and linkages between the weeks. So we go strategically from one week to the other week, and we carry on the learnings so that at the end you take the combined learning to manage groundwater. We gave an introduction to groundwater, what constitutes groundwater, and we discussed the porous space and water gets into the porous space, which initially had air. Now it has water, and that water constitutes the groundwater. The groundwater hydrology, which means groundwater movement, occurs when these pore spaces are connected. Okay. Breakup of groundwater and total water budget. We showed this example from FAO, where you saw that all water is 97.5% is salt. So if you take 100% water, 97.5 percentage is salt water in oceans, only 2.5% is fresh water. Of the 2.5%, only 21% is usable through groundwater and easily accessible surface water. So surface water is only 1%, which is your lakes, soil moisture. Soil moisture can also combine into the top surface. Okay, so the easily accessible water could be 1%, whereas the 20% is groundwater. Of the 20% groundwater, only half of it can be easily accessible. So if you run the numbers, anywhere from 0.5% to 0.7% of the total water available in the planet is groundwater that can be easily accessed. So of the fresh water, groundwater still is the biggest contributor. And so that is why there is tremendous stress on groundwater for agriculture, domestic use, industrial use, you name it, groundwater is being exploited. So if we don't understand the relevance of groundwater in the overall budget, we are losing the groundwater. Think about if you pull the water out and water the plants, or you use it for industry. It goes back as precipitation through evapotranspiration, right? So you apply it through the plants, it evapotranspires, goes to clouds, and then forms precipitation. Where does the precipitation go? Is it going back to the groundwater? Not. It goes back to rivers and lakes. So you have depleted the groundwater. You're not putting back the water, but you are relocating the water as surface water at a much faster pace, which took a long time for groundwater to recharge. So increasing demands are occurring. There is tremendous increase for groundwater because climate change is impacting the world. There are many floods, often floods and droughts. So let's take an example. If you have floods, the whole city is flooded, which has bad water on it. Which water are you going to drink? You're not going to take that water and purify it and drink it. People go to wells because the flood water takes time for it to pollute the groundwater. So if I want to drink during a flood, I would rather go to the groundwater, take it, purify it, and drink it. If you're taking your flood water, it can be contaminated. Then come to the drought. As the name suggests, there's no rainfall. There's no water in the surface. So how do you irrigate? How do you drink water? You have to go to the groundwater. So in both extremes, groundwater is kind of a mitigation and adaptation tool. It creates a buffer for you. Okay. Animals do not have that luxury. If they don't find water, they have to migrate. So you see elephants migrating along the Western Ghats. You see animals dying, walking kilometers without water. They cannot dig and then get water. They find for a water hole. A water hole is somewhere where the groundwater comes in and discharges. So it is very important, groundwater, in the terms of climate change. The water stress has increased tremendously across. The baseline water source shows that most of the countries that are under agricultural livelihood options are staring at water stress either high or extremely high. And when there is water stress, people go eventually to the groundwater, assuming that it is an unlimited supply of water. So what initially was stopping them from taking groundwater? The technology was not good enough. You had pumps that can only pull water to a couple of meters. The process was expensive. You have to put the bore well, you had to put a pump, energy to pump the water was all expensive. Right now, it is the opposite. A borehole can be drilled at any location just by a rig which is put on a back of a truck. Initially, it was a big lorry which would come dig a hole or dig a rig and then put the borehole. But now I've seen very small size trucks with high power machine that can drill anywhere in the urban city, put your well and then go ahead. Same way, the pumps have become more efficient, more powerful, and less expensive. So both sides, it is hitting the groundwater. The easy access and cheap pumps that can literally pull all the water out. Okay. So you have pumps on one side, and then you have access to groundwater on the other side. One more aspect I will throw in here. There are low cost energy options for pumps, diesel power pumps, solar power pumps, you name it. There are multiple different power sources for groundwater now. So all would eventually get in and take all the water out and do not want to put it back in through artificial means or natural means. And that is one aspect we will be covering in the lectures. Let's take this debate with data. Okay. So in this paper, what you see is a groundwater irrigation map. And you see the percentage of area, almost 100% in Gujarat, Rajasthan, Punjab, Haryana, and your Maharashtra, the Vidarbha regions, the dry regions, some parts of West Bengal, even along the Ganges. You see a very heavy percentage of area is irrigated by groundwater. It could be the double crop, triple crop. Okay. So, but still, irrigation is happening. And even if it is one time, you can put it as 100% of that area is covered by groundwater irrigation. Is this reflected in other means? Yes. Let's take the net area irrigated from different sources. You could see from 1950 to 2010, and the net area irrigated initially was with canals. A canal is a distribution system through a dam. So you would construct a big dam, a large irrigation dam along a river, and then water would be stored. Once water is stored up to a particular level before the Rabi season, which is before non-monsoon season, they would slowly release water in channels to areas where farmers have procured land around the channels for agriculture. It doesn't go to every farm. Okay, wherever the channel goes, it will give the water. You can put a lift irrigation or you put a pump and then take the water. That is up to you. But the channel doesn't go to every farm. Okay. So what has happened is the canals area has increased from 1950s. That was the good revolution which was happening. But then it stopped. It didn't increase much. Same way, your tanks, the tanks which would store water and then distribute it, or store water and then you pump it, also did not increase. In fact, it decreased. What has increased is your tube wells. The other wells are your shallow wells, which is your top part of your groundwater. The shallow wells are not taking much water, but it did increase from 1950s to 2010, little bit, and then stagnated. What has happened and is still continuing to happen is the access to tube wells. Tube well irrigation has boomed like suddenly, and it just exponentially increased, and it's going at a very, very alarming and unsustainable rate. Okay. So where, and then this is the distribution of energy sources, which state uses what percentage of the energy is used by different sources. I was talking about solar. So you have solar pumps, windmills, diesel, electric pumps. Manual is when you step on it or cycle it and take water, or you can also have animals going around and then pumping. So what is more important is to understand the area irrigated by tube wells has tremendously increased. And these two are groundwater resources, whereas these two are surface water. So on the overall, groundwater use has increased tremendously. This doesn't look good for the water stress image. So 44% of India is looking at high to extremely high water stress as per WRI. And that areas where they've demarcated coincide exactly with your groundwater map. So this is a different data source, this is a different data source, but what matches with them is that the water, maybe the surface water has already dried out. And that is why they have been excessively using groundwater. And you could see the same regions having more groundwater use or abuse, I would say, because it is at overexploited stage. What do you call overexploited is if you have 100 rupees put in your bank, you're taking 120 rupees out. So you're taking more than the water that came in. Okay, and at a quicker rate. So your 100 rupees would have come after you worked hard for 1 month, you put it in, and then you take it and buy something within a minute. It's not going to be used for the whole month. That's what I'm trying to say. And also excess 120. So you're actually eating in your deposit, or you're eating as a credit, which you have to eventually fill the next month. Groundwater works in a similar way, except that your account is leaky, which means your 100 rupees doesn't stay there. There are some leaks which leak out, okay, like an interest, like a credit card interest. So it is very, very important to understand that if you have a water stress, you should not over stress your groundwater. And if you are using your groundwater over than the recharge rate, there has to be some mechanism to put back water into it or reduce your consumption. That would be my aim to drive across this lecture when we finish. Let's do the other comparison. If you look at this area and this area, it matches. So wherever the groundwater irrigation is happening 100%, it is overexploited, which means it is going beyond the natural recharge rate. This is highly unsustainable. So this is a Central Groundwater Board report, and this is another studies report. So if you look at that and you look at where areas are, this could be your agricultural data, okay, agricultural census data, irrigation department data. What you could see is wherever the blocks, wherever the spaces, which is 100%, matches almost exactly with your overexploited blocks in India as per 2017, which is the latest CGWB yearbook. The other point I wanted to take away here before we conclude is that groundwater takes its time for recharge. It doesn't recharge fast. You can put a pump and take the water within a month, or your Rabi season is 3 months. But the water that comes into your pump will take 1 year. So whatever water you used from the previous year, you cannot use successfully within a couple of years. So that is what has happened because of the technology and development in pumps. You have put the pumps, you are using the water, yes, but is it an annual water? No, it is a water that has been stored for years. So you could see that some aquifers or some storage units, the water takes days and years to come, whereas some units, it would take centuries, and some unit would take millennia, 1,000 years for the water to come. And all these have been proved through groundwater dating studies, wherein radioisotopes have been used to date the water, like carbon dating, and they have found that the water that in particularly very deep locations have taken 1,000 years to recharge. So with that, we're going to conclude on a driving statement for the need for this course. Groundwater occurrence is limited, and also your food production is increasing because the population is increasing, tremendous stress on the farmers. So what can they do? They have to eventually go to groundwater aquifers to take the water, irrigate, and then feed you. So the growing population puts tremendous stress on increasing the food production in the country. So don't waste food. And also coming back, the farmers have no choice but to, if the situation continues, like you have to eat rice, you have to eat paddy and other things which are consuming sugar, for example, too much water, then they have to get at groundwater aquifers and then pump it. Groundwater recharge takes a long time, so it is not as quick as you pump, the water gets recharged. Groundwater is sustaining livelihoods because farmers, industries, etc., they take this water for their use. Even urban centers, when the public supply through pipes is failing, they take groundwater to support their livelihoods and sanitation. Groundwater is a buffer to climate change and serves as a tool for mitigation and adaptation. It is one of the best, I would say, tool which is available. And India is the highest groundwater extractor in the world. It extracts almost 245 kilometer cube, which is more than the combination of the next two countries, which is US and China put together. So let's think about that and see if this course is very, very important and needed. With this, I'd like to conclude the course for the first week, and the introduction part is over, and we will be jumping into the specifics on groundwater hydrology in the weeks to come. Thank you.